In this video, we are going to look at undecidable languages and the Turing acceptance problem. In particular, we are going to look at the famous Turing machine halting problem and show that problem is undecidable. Okay, first, let's look at how many Turing machines there are. Okay. So first, we are going to look at encoding schemes that a description of a Turing machine can actually be encoded into a binary string. For instance, we can simply use ASCII encoding method because your description of a Turing machine is made up of remember that we have the transition functions. We have transition function is just a finite table, which of course made up of a bunch of symbols, subscripts, maybe superscripts or parentheses and commas. So these can actually be easily encoded using ASCII. And then you have a set of finite states. You have a set of alphabet symbols. You have a set of tape symbols. So all of these can be easily encoded using ASCII encoding. Of course, there are many other ways to encode a text, right? So a description using text into a binary string. So your description of a Turing machine is simply a piece of text, okay, which can be easily encoded into a binary string. So then we just fix a encoding scheme. Then under this encoding scheme, all Turing machines can be encoded into a binary string, and a binary string can be can be thought of as an integer. Okay, so now we make a connection of a description of a Turing machine to integers, and different descriptions of Turing machines will correspond to different integers. So because the encodings are different. All right, hence we know immediately that there are countably infinite Turing machines. You could have infinite Turing machines, but they are countably many. Okay, countably infinite. So because they correspond to integers. And then when you are given an integer, then you can decode it back into a description of a Turing machine. Okay, under this encoding, then we know that the number of Turing recognizable languages is countably infinite. Okay, so then, we also know that a decidable language is Turing recognizable because decidable simply means that the language is decidable. There is a Turing machine that decides it. There's a decider that decides it, meaning that on any input, this Turing machine will always halt. And when it halts at a accept state, then that means that that input belongs to the language. If it halts at a reject state, then that input belongs to the complement of that language, or it doesn't belong to that language, right? So that a decidable language is Turing recognizable. So now immediately we have the following result, which says that some languages over the binary alphabet are not Turing recognizable. Okay, so now we first establish the fact that there are languages that are not computable in any sense. So in other words, even not Turing recognizable, because we sort of know that the decidability is a more stronger it is a stronger sense of computability than Turing recognizable. Now you have languages that are not even Turing recognizable. Then later we are going to come up with concrete languages that are not Turing recognizable. Okay, so the proof is by diagonalization, which is a technique that we talk about during mass reveal. At that time, when we show that the set of real numbers is not countably infinite, or is not countable, that we actually constructed so we prove it by contradiction using diagonalization. Okay, so you may want to go back to the mass reveal that we talk about in the first video of this class to refresh your mind. Okay, so now here we're going to use the diagonalization. So it's a proof by contradiction. So what that means here is that now first we let x1, x2, blah, 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 okay, be an enumeration of all binary strings. Okay, for instance, we can list all binary strings following the lexicographical order. What that means here is that we fix the lengths, like n is equal to 0, 1, 2, and 3 under each length. Then we enumerate the strings of that length, such as using lexicographic order. It really means a dictionary order. For instance, if we are talking about binary, so then when n is equal to 2, the lexicographical order would be 0, 0, 0, 1, 1, 0, 1, 1. And when n is equal to 3, the lexicographical order will be 0, 0, 0, 0, 0, 1, 0, 0, sorry, one more 0 here. 0, 0, 1. 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so that means we fix the length first, and then we enumerate all binary strings with their lengths. So then we can enumerate all binary strings. So we prove by contradiction. That means suppose all languages. So let's say just suppose all languages now, first of all, we know that all Turing recognizable languages are countably infinite, countable. Right? So so what we are trying to do now here is that to show there is a language that cannot be Turing recognizable means that I can construct a language under any enumerations of all languages. Okay, so enumeration means it's countably infinite. Okay, so then suppose that all languages over sigma were countably infinite. So let's just call them L1, L2, blah, 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 because any Turing recognizable languages, I'm sorry, all Turing recognizable languages are countable, so which will be a subset of this L1, L2. So we construct a new language L using diagonalization in the following way. So for each I, for each integer I, now think of that I is your index. So for that I, we're gonna look at xi. So if xi is in L, then I will just make we construct a new language L. So if xi is in Li, then I will make xi not in L. If xi is not in Li, then I will make xi in L. So in other words, so this L is constructed as follows. Okay, so again, if xi is in Li, then I will make xi not in L. So I'm not going to put anything. I'm not going to put xi in L. If xi is not in Li, then I'm going to put xi in L. So we construct this language L. And since we assume that all languages were countably infinite, so that means that L, since L is a language, that means that L is an integer j such that L is equal to Lj because it includes all languages and L is a language, so we must have this. But then we are looking at this index j. Then we want to know whether xj is in L, which now is Lj. So then, of course, xj is in Lj by construction of L. Now, Lj is L. By construction of L, that means that if xj is in L, then xj is not in Lj. But then L now is Lj, so it is a contradiction. Okay, and similarly, if xj is not in L, which means xj is in Lj, but this L is Lj. So really we get that xj is in Lj if and only if xj is not in Lj. So this is a contradiction. Hence, there must be a language that is not Turing recognizable. Okay. So what that means here is that there are languages that are not computable, okay, in our sense. All right, so now let's look at a concrete problem. So earlier we just say that there exists a language that's not Turing recognizable. Now we're going to see a concrete example that is not Turing recognizable. But first, we're going to show a language that is not decidable. So this is called the halting problem. So this is one version of Turing machine halting problem. So we call it A sub Tm be the encoding of a Turing machine and the input X to that Turing machine. And this M is a Turing machine and accepts X. So for each of these pair, now this left angle and the right angle represents that it is an integer, right? So this is just encoding. When you have an integer, because under the fixed encoding, you can decode this integer back to a pair, which the first portion is a description of a Turing machine. The other portion, the second portion, is the input to that Turing machine. And if that Turing machine accepts that input, then we are going to put this whole integer, this is an integer, into this set. So then, so this is a acceptance problem or a halting problem. Then ATM is Turing recognizable. Okay, so to do so, the proof is straightforward. To do so, we just construct a Turing machine U, which takes this encoding, a pair of M and X under the fixed encoding as input. And this U is also referred to as a universal Turing machine, just like our computer, right? So our computer takes a program, runs a program. So when you write a program, you think of that program as a Turing machine, so that you store that program in your computer, and then when you run it, of course, you take that take that program, and then take the input to that program and execute that program on that input. So of course, your computer then is a universal Turing machine, your universal machine. So similarly, we can have a universal Turing machine where your program is a description of a Turing machine. Okay, so, and then, so what we are having for this use, it takes input m comma x. So we decode this integer to get a Turing machine m and a binary string x as an input to m. And then u simply runs m on this input x, just like your computer would do when it executes a program on an input. Okay, so then this u accepts. So this is how we construct this u. So we let u accept this input m comma x if m on x ever enters its accept state and rejects this input if m on x ever enters its reject state. If it doesn't halt, then u simply loops. It just keep running. Okay, so we don't know when it's going to halt. You just keep running. When it halts, if it enters accept state, we accept the input. U accepts the input. When it halts, otherwise, when it halts, it's in a reject state, then it rejects the input. Otherwise, okay, just keep running. Hence, we know that this U is a Turing machine, okay, and this U will accept this input, m comma x, when m is a Turing machine that accepts x. Okay, so that hence we have this. So that establishes the fact that A sub Tm is Turing recognizable. So in order to come up with a concrete example that is not Turing recognizable, the next thing we want to do is to show that A sub Tm is not decidable. Hence, the complement of A sub Tm is not Turing recognizable. So that is the roadmap we're going to take. Okay, so now we show that A sub Tm is not decidable. So again, we're going to use diagonalization. So of course, we first let M1, M sub 1, M sub 2, blah, 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 be a fixed enumeration of all Turing machines under a fixed encoding method. Okay, so then suppose that, okay, A sub Tm were decidable via a decider D. So this D is a Turing machine. Then that means that D on input m comma x under this fixed encoding always halts. Okay, so that's what decider means. And D accepts m comma x encoding of m comma x if and only if this encoding of m comma x belongs to A sub Tm. So this is a straight definition of D. Okay, because that's the decider of A sub Tm. So now we're constructing a new Turing machine, let's call it D prime, such that on input I, so this Turing machine just takes a input, it's an integer, okay, I is input, decodes it, okay, decodes it, so that means, well, you can think of it on this integer I, this is input, and then we will simply let D prime simulate D on this input. So this is M sub I comma I, okay. This, of course, it is a so this M sub I just means the I's Turing machine, and this I is the input. So we take the Turing machine itself as its input. Okay, so that's basically what it means here. So then we are going to run D. So D is a decider. So this is a input. So D is a decider on A sub Tm. So on this particular input, it will either, so if this input belongs to A sub Tm, then D accepts it, otherwise it rejects. So this D prime will do the opposite. So D prime runs this, and if D accepts, okay, D prime runs D on this. If D accepts, then D prime rejects I, otherwise it accepts it. So it's just the opposite. Because D is a decider, so D prime is also a decider. So D prime now is a Turing machine. So this is a Turing machine, it always halts. Then, because D prime is a Turing machine, there must be an index J, which such that D prime is equal to Mj, because this M1, M2, blah, 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 is an enumeration of all Turing machines. And D prime is a Turing machine, so D prime must be in this enumeration. That means that there must be a J such that D prime is equal to Mj. Hence, Mj accepts J, okay, if and only if, by construction, that if and only though Mj accepts Mj, which is D prime, on its input J, accepts it if and only if D rejects Mj comma J. But then when D rejects Mj comma J, it means that Mj rejects J, okay? So that's what D means, okay? So this is what D means. So that really gets you a contradiction because you're saying that Mj accepts J if and only if Mj rejects J. So it cannot happen, right? So it's impossible. Hence, our assumption that A sub Tm were decidable is incorrect because everything else is correct only when you have this, your assumption implies everything, then implies a contradiction. So that means that your assumption is incorrect. That means then ATM is not decidable. Okay, so that is the proof. Okay. Right, now let's look at co-Turing recognizable languages. Okay, so in other words, we're going to look at the complement of a language. So we're saying that a language L is co-Turing recognizable if the complement of L, denoted by L bar, is denoted by L, so we call it L bar or L over 9, is Turing recognizable. Okay, so the theorem says that a language L is decidable if and only if L is Turing recognizable and co-Turing recognizable. So in other words, this really means that if and only if L and L over 9 are both Turing recognizable. Okay, so that's actually pretty obvious because when language is decidable, it means that you have a Turing machine such that on any input, it always halts, and if it enters an accept state, and this input belongs to L, otherwise, that means it enters a reject state, and the input belongs to L bar. Okay, so then, so you just so that really, because of the halting thing, so you can now construct a Turing machine to accept L bar. All right, so this is a proof. Suppose that L is decidable via a decider D, then L is Turing recognizable by itself because D is decidable. Now, so this is a now. Now construct a Turing machine M that accepts X if D rejects it. So this then accepts L bar. So then this is one direction. So if L is decidable, then both L and L bar are Turing recognizable. Now we prove the opposite direction. Suppose that both L and L bar are Turing recognizable. So which means that there are Turing machines ML that accepts L and NL prime that accepts L bar. So now we construct a new Turing machine M as follows. So on any input X, M will execute ML on X and ML prime on X simultaneously. So that's what this means. So how do you do simultaneously? Of course, you could M runs ML on X for one step, and then run ML prime on X for one step, and then continue ML on X for another step, and then ML prime on X for another step. So this is a concurrent execution. So because we know that one of these execution will halt eventually, so when it halts, then we will know whether X belongs to L or not. Okay, so M halts if one of these two simulation halts. Okay. Moreover, M accepts X if ML accepts, and M rejects X if ML prime accepts it. Okay. So that means that L is decidable. Okay, because this M always halts and can tell you whether on any input X it belongs to L or not. So that shows that L is decidable. Okay, so finally, then we can establish the fact that the complement of A sub Tm is not Turing recognizable because A sub Tm is not decidable. Okay, so that is a concrete problem. So in other words, if we write it, A Tm bar means this. So this has a encoding of a Turing machine and an input to M. And then M doesn't accept X. So it doesn't accept could mean it rejects it, or could mean it runs into infinite loop. Then it will never accept, it doesn't accept X. I mean, whenever N accepts state. So for this, so for any pair of these, and then you want to determine, you want to find out whether M doesn't accept X, it's not even computable. Okay, so this is not computable problem because it's not even Turing recognizable. All right. So now we have some ideas about computability. So what is computable in the sense of what is Turing recognizable, and then what is decidable that you can compute, you can recognize both L and its complement. Okay. And next, then we have a hierarchy. So this, in terms of computability, we have this hierarchy. All right. So really we have even bigger ones. So this is non-theorem recognizable. Recognizable. But for this, so everything that's computable will be computability. So we know that non-Turing recognizable means not computable at all. So for anything that's computable, we have this hierarchy. So regular languages are computable, context-free are computable, decidable languages are computable, and Turing recognizable languages are computable. And then regular languages are strictly included in context-free languages, which are strictly included, which is, in other words, which is a proper subset of decidable languages, and which is also a proper subset of Turing recognizable languages. All right. So that is the end of this video. So in this video, we talk about what is decidable, what is not decidable, and what is Turing recognizable and what is not. We focus on what is not decidable and what is not Turing recognizable in this video. In the next video, we're gonna come up with more non-decidable languages. Okay. See you next time.